All right, okay, let's go through these. Let's go through these. So, if you remember, on Monday, we started looking at this idea of an inverse matrix. Now, who remembers why we started looking at inverse matrices? What was the kind of premise for looking at them? Yeah. We were looking at the division of matrices, right? So we said, we can't do division as such, but we can think about division in terms of multiplication, okay? For example, and I used to think this analogy, if I wanted to write 6 divided by 2, okay, but if I lived in a world where division didn't exist, I could still work with this. How?
6 multiplied 1/2.
Absolutely. So division and multiplication are really the same thing kind of in disguise. And you remember the relationship between this 2 and this 1/2, the relationship between these two, which allows me to change a division into a multiplication, and Vicky Verky, right? What's the relationship between the two? They are inverses, right? Okay, so we looked at this idea of an inverse as a gateway into thinking about division in terms of multiplication. Because, of course, we know how to multiply matrices together. We did loads of work on that right at the very beginning, right? Okay, so if we can understand this idea of an inverse, then we're doing a type of division. Okay, it's our kind of gateway into matrix division, even though that's not really a thing. Okay, all right, good. And you remember, I just gave you this recipe. I said, if you have a matrix with 4 elements, so A, B, C, and D, okay, then the inverse of that matrix will be 1 over the determinant of that matrix. You remember how you calculate determinants? Okay. And then you flip the leading diagonal around. So you see A was there and D was there. On the inverse matrix, D ends up there and A ends up there. So you see they've kind of flipped around. Okay? And then the other 2 elements we just negate. Okay? So if they're positive, we make them negative. If they were negative, we make them positive. Okay? And I just gave you this. Okay? It's not that difficult to prove, and I thoroughly recommend that you go away and check this out. Because, of course, if I take an inverse matrix, A inverse, and I multiply by the original matrix, what should that be equal to? Can anybody remember?
1.
Should be equal to the equivalent of 1 in matrices, which is the identity matrix. Fantastic. Do you remember that? Yeah? So yes, it is like 1, but it's just with matrices instead. All right? Okay, good. So yeah, you can always use this property to prove that if I take this and I multiply it by this, then I should get the identity matrix. In other words, I should get 1, 0, 0, 1. Okay? So, okay, done enough talking. Let's look at finding the inverse of that matrix. I've given you enough time to kind of think about this, okay? So if I want the inverse of this matrix, first of all, I need to think about the determinant of this matrix. So what's the determinant of this matrix? What's the determinant of this matrix here? Good, so we times the leading diagonal together, 3 times 6.
18 minus 50.
Good, and then we take away those 2. So we take away 1 times 15. Okay, so I'm just going to write it like that. That whole denominator there is the determinant of my matrix. Is that okay? Okay. And then I take my matrix, so this matrix here, and I flip these 2 elements around. So I swap these 2 elements. So in other words, 6 was here, so now it ends up here on my new matrix. Is that okay? And then 3 was up here, so now it ends at that position there on my new matrix. Then the other 2 I just make negative. Okay, that's what my formula tells me. So that's negative 15 and negative 1. All right. So that is my inverse matrix. I'll just do a bit of tidying up. Okay. So this is 1 divided by what? What's 18 minus 15? 18. Sorry. 24 minus. What am I doing there? Oh, it's 3 times 6. That's why. That's it. So 18 minus 15. What's that equal to? It's equal to 3. And then I leave that alone, so 6, negative 1, negative 15, and positive 3. Fantastic, happy with that? Okay. Then I just multiply every element through by a third. Okay, I could leave it like that if I wanted to. I'm just going to tidy it up even further by multiplying through by a third. So if I multiply this element by a third, it becomes 2, right? 6 multiplied by a third is 2. Then if I multiply this element by a third, what does it become? Good, negative a third. If I multiply this one by a third, negative 5. And multiply this one by a third, just 1. Okay. So what I've done here, if this is my original matrix, 3, 1, 15, and 6, okay, my inverse matrix is equal to this. Okay. Now how can I check that I've done the right thing here? So if I take this and I multiply by this, it should be equal to the identity matrix. Okay, so let's check this out. If I take 2, negative 1/3, negative 5, and 1, so in other words, that matrix there, and I multiply by this matrix here, okay, by the way, in this case, it doesn't matter which order. So just take this element here, 3, 1, 15, and 6, okay. Let's check it out. If I multiply those two matrices together, what do I get? Can we check out to make sure we get the identity? So 2 times 3 plus negative a third times 15. Okay, so 2 times 3 is 6, and then I'm taking away 5, because 15 divided by 3 is 5. So 6 take away 5 is equal to 1. You happy with that? Okay. Let's go for this element here then. This element here will be first row, second column. So first row and second column. 2 times 1, 2, plus negative a third of 6, which is 2. So I'm taking 2 and I'm taking away 2. I get 0. Looking good. All right, let's go for this element here, which is second row, first column. Second row, first column. Negative a 5 times 3, negative 15. 1 times 15, 15. Okay, so what's negative 15 plus 15? It's 0, dead right. Check this element here. So it's going to be this row and this column. Negative 5 times 1, negative 5, and 1 times 6, 6. So negative 5 plus 6 is 1. Okay, so we've done the right thing.
But